So we're filtration model. In order to begin designing our mathematical model, we decided to learn more about the filters in general, specifically the fundamental filters, the slow sand filter, the rapid sand filter. The slow sand filter operates by using a biological film that grows naturally on the surface of the sand. As the water passes through the biological film, the impurities or the particles within the water are absorbed into the film. While this sounds effective, Monroe actually pointed out by using a coli that biofilms don't actually play a significant role in particle removal, or if they do, it's relatively insignificant, as the composition of the biofilm cannot actually ingest the larger pathogens. Additionally, the thickness of the biofilm requires a stronger force to push the water through the filter. This idea is known as head loss. However, the slow sand filter still appeared to be effective, which meant that the removal mechanism was independent of the biofilm itself. Now we focus on the rapid sand filter. The rapid sand filter generally works the same as a slow sand filter with a clear advantage. Due to the lack of a biofilm on top, the head loss increases linearly and the filter itself is easier to clean, thus saving more time. However, the process in which filters do get rid of particles, which are significantly smaller than the pore itself, is quite astounding and critical to understand for future research. Our goal is to build a mathematical model to quantitatively represent how that happens.
The SAG rapid sand filter is a novel cell backwashing filter invented by the Agua Clara team. Its unique stack geometry allows it to use the same flow rate for the filtration and backwash cycles, without expensive pumps or elevated tanks required to backwash conventional rapid sand filters. In addition, a SAG filtration system requires a much smaller footprint than a conventional filter to treat a given flow rate. For the past stars team, they decided to run one filter at a time for simplifying the system. The main goals of the spring 2020 team was to decide the optimal sand grain sizes that maximize the filter performance and failure time. However, due to the insufficient lab time given last semester, the team was not able to conduct as many experiments as planned. Therefore, we want to switch our focus on the theoretical part of the mathematical model this semester.
From previous research, we determined that rapid sand filters have an active filtration zone. What we mean by this is that during the process of filtration, only one pore or regions of pores is being in use. As shown in the image, there's only a line of pores that are involved with removing the particles at a given time. This prompts us to further investigate into what's happening at each pore. We believe that the streamlines of the particles converge and either pass through the minimum constriction of the pore itself or hit the side of the wall and remain on the edge of the constriction site with the wall and attached to other previously deposited particles. After a certain point, the maximum bond force causes the flow constriction to reach a minimum diameter of the constriction. This causes the accumulation of particles that stop within the pore and move on to the sequential one.
In order to build a model, we will need some hypotheses based on the filtration theory. First, as a pore begins to fill, the flow constriction area will become smaller, resulting in a higher capture efficiency. However, if the pores are clogged, the sand filter will be ineffective as soon as one layer of pores is filled. Therefore, some other possibilities might address the problem. We hypothesize that flux cannot attach to the filter surfaces when the fluid drag on the flux exceeds the strength of the bonds between the coagulant nanoparticles and the particles and pore surfaces. As a result, as pores become smaller, they become more difficult for the incoming flux to attach. Upon further investigation, we learned that when the drag force equals the bond force between coagulant particles in the water, the radius of the pore will start decreasing. So the team will approach the performance of evaluation of the rapid sand filter with the simplest model possible. As a result, for the filter media, we assume each particle as a homogeneous perfect sphere, the uniformity of which throughout the model can make our evaluation easier. Second, one type of particle is considered in the model since we want to mimic the conditions of the lab-based stars filtration model. For the size of the particle, we adopt a size of 0.45 millimeters, the sand grain size used commonly in the Agua Clara plant. In terms of the arrangement of particles in the filter, we assume perpendicular SAG lines of particles. The particles are perfectly aligned with one another in a way that preferential flow caused by geometry of the filter media can be eliminated in the preliminary phase. Lastly, the team also assumes the filter cross-section to be a perfect circle, and the particles are arranged in a way that one layer of section will be filled to its maximum capacity. We keep the flow rate as a variable in equation. Given that we are interested in the probability of the particles hitting the wall in the dirty filters within a 20-second time period, the team decided to adopt the uniform velocity profile. For the maximum thickness of particles collected in the interested area, we assume there will be only one layer of the particle. Maximum thickness of the interest volume therefore equals the diameter of the treated particles. We also assume that all particles are distributed evenly around the pore with a void space of 40%. In this case, we can calculate the projected area in terms of the bound force mentioned in the section, in the hypothesis section. We assume a value of 10 nanonewtons bound force.
So from previous research, and as Valentina mentioned, we were able to determine that the bond force has a magnitude that is on the scale of nanonewtons, which we assume to be around 10. Now, in order to construct the model, we need to estimate the probability that the particle actually hits the wall. With the probability that the particle hits the wall, we need to use the following parameters: diameter of the flux, the flow rate through the pore, and the uniform sand grain size. As we see on the slide, a washer is actually a very good model for the minimum constriction of the pore once the radius stops decreasing. Using Python and the parameters with estimated values, we can get the maximum constriction velocity and use the Darcy equation to determine the radius as a function of time. We can do this by using 20-second intervals and get the radius at that point, and then decrease the time intervals to eventually get a better representation of the radius decreasing as a function of time.
So we had our fair share of struggles this semester. Aside from everything being completely online, I would safely say that none of us have ever explored this field of theoretical math or knew how to go about doing it. For starters, the one thing about research is that you will never have all the material and resources necessary to solve the problem at hand. This proved to be a big challenge for us as we struggled coming up with equations to apply to our work and had to derive them on our own using our own knowledge. However, we did face this challenge head on and did as much as we could. We also met with Monroe at the beginning of the semester, where he gave us some guidance on how to approach our semester goals. And after, we worked to get an equation, but unfortunately ran into a lot of complex mathematical stuff that wasn't familiar to any of us. We tried to get any results whatsoever, but we were having difficulties. We met with Monroe towards the end of the semester again to explain what was going wrong, and he said that he accidentally led us down the wrong path. We wanted to make sure that we understood everything conceptually and everything that was happening in our model before we started working on doing the actual hard math. We knew that if we wanted to make any progress with the math portion, we must first understand what was going on theoretically. We developed our strategy in first modeling a singular pore and scaling up from there. That, however, would prove to be the hardest part of anything we had to do. We decided that in order to model the pore, we would have to model the radius decreasing as a function of time as water was passing through. We know that once a single pore is modeled, we could scale that up to model a perfect stack of pores, and then scale that up again to model the total number of pores in the filter. Future work for this team will include picking up where we left off in our analysis of the radius of a pore, and then scaling up to the entirety of the filter. Thank you guys so much, and have a wonderful rest of your semester.